Okay, so the capit is, so we start with even dimensional space-time, and then we want to capture how the partition function transform under the background gauge field. Partition function under the gauge transformation of the background gauge field. And the cost of the gauge transformation is called anomaly. And this omega to n is some cohomological, can be captured cohomology. And to capture this cohomology, we start with so-called anomaly polynomial, which is 2 degree higher than the space-time dimension. So this is called anomaly polynomial. And then we solved so-called descent equation, which is I to n plus 2 is locally given by so-called Chern-Simons term. And then gauge variation delta is the delta B is the gauge variation, and omega to n plus 1 is the d omega to n. So you solve this descent equation, and then delta B square equal to 0 is Wessels-Zumino consistency condition. Okay, so that's what we tried to do last time. And essentially, we need to. So this anomaly polynomial is written in terms of Pontryagin number, and also so this I to n plus 2 is roughly written like this way: ck trace of r to k trace of f. What was that? N plus 1 minus 2k. K runs for whatever 0 to whatever n over 2, and this is just a coefficient. That's what we have done. And we can just capture this one is the gauge, capture gauge anomaly or gauge field. And that is often related to Chern class. And then this one is the gravitational field. And this is since the holonomy or bundle of the real dimensional manifold, cotangent bundle, tangent bundle is the Pontryagin number. Pontryagin classes. So that's what we have learned last time. And then, so those are called characteristic classes. Characteristic classes captured by, so those are anomaly polynomial. And depending on the field content, anomaly polynomial received, so it's chiral field. Chiral field contribute. Contribute to anomaly. So type 2A has a gaugino has plus minus and lambda plus minus. So this is not chiral field. Plus is, I don't know, it depends on how you call it. I don't know which one I call it, left and right, I don't remember. I call it plus is right-handed. So the both right and left-handed, both spinner exist. So it's anomaly free. Anomaly free. But the 2B is non-trivial because 2 times plus m, 2 times lambda minus d Latino. So that, and also self-diapone. There is self-diapone up here. So DC4 is G5, and G5 has is under this one. Self-deal. And this is also chiral field. The way to look at why this is chiral field, essentially, if you look at the vertex operator G5, in fact, G left hand gamma mu1 dot 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 mu0 mu5. Is it 5 4? No, mu 4. Whatever. Psi r, and both has the same chirality to define the G5. So I mean, vertex operator that corresponding to the, I mean, G5. You already learned from homework is actually left and the right spinner. The Ramond ground field that corresponds to Ramond. I don't. You remember, right? So this psi is not the space-time. It's the two-dimensional worldsheet with the that corresponds to the Ramond ground state, and both have the same chirality. Therefore, if you do the chiral transformation, you get the anti-self-dual form. So therefore, so this will contribute to the anomaly, and we computed from some previous case. We computed. So this is the gaugino, so contribution from complex gaugino, and this is the di Latino, and then this is G5 contribution, and then if you do the computation. So I12 of type 2b. So it's a really crazy number, but it's a really complicated one. But if you do the computation, 2 times 1/2, I3 half 12 r minus 2 times 1/2, I1 half 12 r. So 12 means. What does 12 means? What does 12 means? Why 12? What does 12 mean here? What does 12 mean? What is the space-time dimension of the type 2b string theory? What's the dimension, space-time dimension of type 2b string? Superstring. What's the critical dimension of superstring? 10 dimensions. So this is 10 plus 2. So anomaly polynomial is 2-dimensional higher. So 12 means 10 plus 2. So P4 is a degree 4. 4 times 3 is 12, right? And this is 4 plus 8. And this is 8. So then there's some typo here. So which means, where does typo? Oh, this is 3. Actually, 3. 12 dimension. So everything 12 as a degree 12. Degree 12 character classes, and then plus I self-dual 12 R. Okay. So this 2 is really coming from, so this is Majorana condition. Majorana condition. Majorana means some reality condition. You already did this homework. Reality condition you have to impose for Gravitino and the Di Latino, and this anomaly polynomial is complex fermion. So complex Wald fermion. So therefore, to impose Majorana condition, you have to multiply by half. And since we have a 2 copy of Gravitino, right-handed Gravitino, you have a plus. 2 copy of left-handed Di Latino with what Majorana condition. So therefore, and the minus sign is coming from, relative sign is coming from, this is right-handed, this is left-handed. And then plus this one. And if you do the computation, if you just plug in this one, you find. So therefore, type 2b is, if you look at the Green-Schwarz width, then it is called miraculous cancellation. Even type 2b. I mean, so if you look at these numbers, it's a really crazy number. But somehow type 2b nodes, they cancel each other. So here, let's see. I have to mention that the anomaly is for global symmetry. Global symmetry. Anomaly is a feature. Anomaly is feature. Is feature. However, for local symmetry or gauge symmetry, or diffeomorphism symmetry, anomaly is obstruction. Okay. So upper one is called Hooth anomaly, so which it plays a very important role. It's okay to have this kind of phase under the background gauge transformation. For global symmetry, it's totally fine to have such an anomaly. But to gauge it, make it local, so to make it local, you cannot have this kind of phases. Okay? So in particular, gravity is one of the local symmetry. Diffeomorphism. Diffeomorphism is a local symmetry. And we want to preserve this covariant, general covariance as the Einstein told us. So therefore, anomaly needs to cancel. Okay? But we don't need to go to compare omega 2n. Omega 2n is kind of difficult. It's better to go to two-dimensional higher degree to see the cancellation. That's much more convenient. And then we just need to go to anomaly polynomial. Because this is cancelled, if you solve the descent equation, at the level omega 2n, they cancel. That's the case. And let's move on to type 1. So now we go to the type Green-Schwarz cancellation of type 1. Super. Okay, Green-Schwarz cancellation type 1 super. Okay. So type 1 is the type 2b, and then do the orientable projection, and you get type 1. Okay. And then you used to have, so here you have, let's see. So here, we have the 2 times psi and plus minus, and plus, and then 2 times Diratino and C5. But oriented for projection, so one of them will be projected out. So we have only one copy of Gravitino, one copy of Diratino. This is the projected out. Only sorry, not C5, G5. So G5 associated D3'. There is no D3' in type 1. So it's become projected out. Okay, projected out. So therefore, we need to find the anomaly contribution from this one and this guy. So 1983. 1983 algorithms Game and Witten mentioned that if you compute I12, so that the upper one 3/2 minus I12 1/2 is not 0. So type 1 string theory anomalous. Seems to be anomalous. That's what Abelsbaum and Witte mentioned. And then next year, 84, Green-Schwarz. Solve this. I would say, yeah, the puzzle. Yeah, puzzle as follows. In type 1, as we know, is we have 32D9 plus O9 minus that will create SO32 gauge field. But this analysis we did, this analysis why 32 is has to be 32 is really coming from Polchinski's worldsheet amplitude. Sheet amplitude. So this is analysis done by Polchinski by around 88. Polchinski. So essentially what we did is I cylinder, I cylinder. Amplitude cylinder, amplitude of climb bottom, amplitude of Möbius strip, and equal to 0 only when SO32. Okay. But this was the 88. But before then, we didn't know why this. We don't know this analysis. So people already knew that we can add before then. So this is 88. Before then, at the time of Green-Schwarz, type of supergravity has 10D. So we can add the 10D YAMLs term action with gauge group G. So the action of YAMLs are 10. YAMLs, G YAMLs. And trace. So one can add this R1, 9. So we can add this kind of action, but we don't know gauge group G. And this has the super YAML, sorry. D equal to 10 super YAML. Super YAML means gauge field has a content. This is gauge field, and also and gauging. You can have a gauging. So this is chiral fermi actually. It's a chiral fermi. So gauging, I think it's gauging. Okay. And this is P1/2, so that we can just add. We can add this contribution of this I12 RF. Since now we have both this gaugino will contribute to this hexagon diagram. I don't know. So this hexagon diagram. So this in the intermediate loop you have the gaugino will just run. And since this gaugino couple both gravitational field and then also gauge field, for instance, covariant derivative to gauge field should be like this way. action, the kinetic term for this gaugino should be like this way, the usual Dirac term. And this is equal to eta bar, of course, gamma mu, d mu. D mu is essentially partial mu plus 1/4 omega mu gamma AB. Like this way. So it couples both spin connection and the gauge field. This gauge field is just the Yamage gauge field. And omega is really the coupled, just give you R. So just recall that the F2 or F is equal to dA plus A wedge A square. And R is equal to d omega plus omega square. So that's the case. Spin connection, and then A is the gauge field. And so it couples both of them. So gaugino will contribute this anomaly polarity like this way. So once you add this contribution to here, what's going to happen? So that's what the Green-Schwarz did first computation. And then 2 times I20, 12. If you add this one, so let's see. So yeah, 2 times this I 3 half plus 12, and this RF. Sorry, this is only half R because it's a the Latino, it only couples. So this is coming from lambda minus, this is coming from psi m plus, this is coming from eta. Okay? Eta plus. So it should be eta plus. It's a chiral fermat, it's just plus. And everything plus, eta plus. Eta plus. Okay. Chiral fermat. Right-handed chiral fermat. Okay, and if you compute this one, you will get again crazy number. And so I just give you some flavor how crazy it is, but so CH is chunk character. Dim G is the dimension of the gauge group. And P3. Okay, so this is again crazy number. So dim G is a dimension gauge field. Is the gauge group, dimension of gauge group. Okay. Or adjoint representation, or dimension adjoint representation, whichever you call it, it's the same. So, if you are sorry, I think I made a mistake, 9.6. So if you are really keen to the previous lecture, so some students already noticed that this term will cancel. This term will cancel when you choose dim G as the. So we already learned. I mean, so we go back to like historically wrong order. We are doing historical wrong order. So that's why it's easy to notice for us. I mean, I think most of the people would give up if you look at this expression. It's almost looks like hopeless to be zero or cancel. But Green-Schwarz actually are confident about. I think most likely they are really confident that the type 1 will work as a quantum field theory. So first of all, this term dmg 496 when only one g is equal to SO32 or E8 plus E8. That's what they notice first. So this term will drop out. So that's the. So this is already this gauge group already appear heterotic string. So that's why we already knew that it should work, but they just found I think it's just look at the Lee group algebra book and then they found this is the case. And moreover, the problem is so another important thing is that this where's the color chunk? This chunk character of 6 is something you can do. So when G is equal to SO n, G equal to SO n, trace of adjoint representation of f to the 6 is equal to n minus 32 f of fundamental trace of fundamental representation of f to the 6 plus 15 trace of f square trace of f to the 4th, like this way. So as you can easily see, when SO n is equal to this term will go when n is equal to 32, SO 32. The similar thing will happen when G is equal to E8 plus E8. So, so this trace really depends on representation of the gauge field, representation gauge field, and we assume that all the chunk character is an adjoint representation because I mean, Mel's field is the adjoint representation. Like this way. So E8, E8. So of course, the chunk to the 6 is indeed e to the trace of IF over 2 pi. No, sorry. Trace is the in front, right? As far as I recall. Sorry. Let me check. Did I write somewhere? No. Most likely, yeah. I think I should write that e to the trace of like this. So this is the case. So therefore, if you do a Taylor expansion and then this is chunk character and ch of 6 is trace of e to the if over 2 pi, and then you just took the 12 degree. The 12 degree, you have to pick a 12 degree. And that will contain trace of the f to the 6. If you use this fact, it turns out that the following thing happens. So C So this decomposition happens. So when G is equal to SO32 and G is equal to E8 cross E8. E8 cross E8. Okay. So this will happen. So this part, so therefore this part is the purely 6 dimension. So purely degree 6 differential form or differential form or homology group differential form homology group is that homology group cohomology group, but it can be decomposed H2 some element. So this means that some element, let's say R4 which R8. This is inside H4 of H4 homology group H8. Okay, so this is degree 4. This is degree 4 homology groups. Churn 2 is degree 4. Churn 4 is degree 8. Okay, and this is also 4 wedge 4. Okay, degree 4 cohomology group wedge degree 4 wedge degree 4. So in total it becomes 12. Okay. So therefore, so what the Green-Schwarz noticed that the Green-Schwarz noticed, since this term is gone, so this is P3 is purely 12 dimensional. Sorry, degree 12. Sorry, you should mention this is purely degree 12. Okay, because I mean it contains trace of adjoint of F to 6. This is purely degree 12. Degree 12. Differential form. Okay, it cannot factorize into the. This is usually it cannot factorize to the like this form, like this way. This only happens when G is equal to SO8, SO32, and E8 cross E8. This only happens. So this degree 12 is this decomposed degree 4 and degree 8. So the notice that the I12 only can be written which x4 and then y8, okay, where the dx4 is also cross form d8 is d. So that's what Green-Schwarz noticed. When this is the case. When this is the case. Okay, so that's what. So this is a key point of a Green-Schwarz cancellation. So this is really key point because I mean here usually this is purely degree 12 cohomology group. So usually people just write down say x, y, z 12. People usually doesn't. You cannot write down this one is decomposed y8. Both are the cross form. You cannot write down like this way for general gauge group G. Okay. This is only happen when the gauge group is SO32 or E8 cross E8. And this term will be gone for the other type of for SO32 or E8 cross E8. And if you look at the other part, this is degree 4, right? Degree 4. Degree 4, this is degree 8. And this is the degree 8. And this is degree 4. Okay? And this is also degree 4 cube, right? 4 times cube. Okay. And this is degree 4. Degree 8, like this. Okay. So everything factorized at degree 4 and degree 8 only when G is equal to SO32 and E8 cross E8. So this is what the Green-Schwarz observed. If this is a case, one can just cancel this anomaly by so-called counter term. So to see that, first we need to solve so-called descent equation. So we assume I12 is this form, and solve the descent equation. To do that, we assume that that x4 in this case is indeed p1 minus. So this is the explicit form. I don't think it's meaningful to write down the explicit expression. Sorry, I think it's a waste of time. Okay, sorry. The important thing is the x4 is a close, so that locally it can be write down the Chern-Simons like omega 3, and then y8 is also locally Chern-Simons d7. Because I mean we already knew that they are both closed form, so locally it can be written. It can be written like this way. Okay. So in particular, this omega 3 is important, and this is trace of omega d omega plus 2/3 omega cube minus 1/3 trace adjoint. No, 30. 88. Don't have a place to 80. So especially omega 3 is like this way. I mean, okay. So we know P1 is equal to R, which R trace, and this is second Chern-Simons trace of F squared. Yeah, F which F. Proportional to sorry. So therefore, I'm very sorry. So this is exactly proportional to C of 6. Okay, C of 6. Yeah. So therefore, degree 12. I don't know. Degree 12. The Chern character is given by here, and n equal to 32. This will be gone. So you factorize degree 4 and degree 8, and the same thing happened here. Okay, and then so we just write down the following thing. So this is the case, and then I12 is the x4, which y8, and this can be write down the form 2a. One is equal to d omega 3, which y8, or x4 d omega, like this. So I just plug in either x4 is d omega or y is d omega 7. Okay, so it can be written either way. So therefore, we can just take some alpha, let's say whatever, some real number, such that alpha d omega 3, which y8, and plus 1 minus alpha x over 4, which d omega 7. Okay, that's what we can do. Just linear combination. And we solve the descent equation. So let us record what is the descent equation. Descent equation I12 is equal to d omega 11 Chern-Simons, delta omega 11 Chern-Simons equal to d omega 10. And we want to find d omega 10. So in this case, omega 11 Chern-Simons is given by just alpha omega 3, which y8. And then if you add the d on it, d only see omega 3, because y is annihilated by d. And then here 1 minus alpha x of 4, which is omega 7. Okay. So if you add the d on omega 11, it only acts on d omega, because d annihilates y, because it's a closed form over there. And d annihilates x4, but d c the omega 7. That's what you get from in upstairs. Okay. Okay. So this is the omega 11 Chern-Simons. Okay, then let's try to solve this second equation. So delta B acts on the omega 11 Chern-Simons, and then of course this should be d mu 2, which y8 plus like this. So we know that these x4 and x8 are characteristic classes. So therefore, delta x4 is equal to 0. Delta y8 is also 0. So because if you did a gauge transformation, those are all gauge invariant quantity, because those x4 and y8 are gauge invariant. Okay, because it's trace of something, trace of gauge group. So it's a gauge invariant. So even if you act on gauge transformation, BRC gauge transformation, 0, 0. So therefore, delta only can be acts on the capital omega. Okay, and delta only acts on capital omega 7. But solving this descent equation, there must be some mu whose extra derivative should give you the delta omega. So this means that the delta omega 3 is equal to d mu 2. Okay, d mu 2, and delta B omega what? 7, like this way. Okay, so by this integration. So therefore, from here, one can see that the omega 10 is indeed given by alpha mu 2 y8 mu 2 which y8 plus 1 minus alpha what was that? x4 which mu 6. Okay. So that's the case. Okay, so that's so this is an anomaly polynomial for type 1. When g is equal to, so this is an anomaly of type 1 when g is equal to SO32 or E8 cross E8. And the Green-Schwarz notice that this can be cancelled. So this can be cancelled by adding so-called counter term. So this is called Green-Schwarz counter term. Okay, this can be cancelled by so-called Green-Schwarz counter term. So we just had so the alpha anomaly is given by 2 pi actually. Sorry, I think delta normalization is horrible. 2 pi, and omega 10, which is given by 2 pi alpha mu 2 y8 And then we just add we add the counter term, gamma counter term, which is actually called a Green-Schwarz counter term. Omega 3, which omega 7 plus C2, which Y8. So that's we are going to add. Okay. Sorry. So this is a counter term we will add. Okay. So therefore, if you take a gauge transformation, so this is a counter term we will add minus sign. And if you take gauge transformation, we will get as follows: minus 2 pi and 1 minus alpha. So this is called Green-Schwarz counter term. GS counter term. To cancel anomaly. To cancel this anomaly. And if you take gauge transformation, we know that the delta B of omega 3 is equal to d mu 2, which omega 7. And then C2, which plus another thing is coming here. So the C3, which d mu 6, and then another thing is plus delta C2, which Y8. Okay, that's what's going to happen. Okay, so that's what's going to happen. And this is equal to, and then if you do the addition between these two, what's going to happen is as follows. So if you add delta W, so what's going to happen is this delta W plus delta counter term is given by as follows: mu 2, which Y8, minus delta C2, which Y8. Okay, and so therefore, if you just do the honest computation, this is omega. So here you can just add the delta. If you add the delta omega 3, you get the d mu 2. If you add the delta on omega 7, you get the d mu 6. And then we know that the delta y is equal to 0. So the delta only can act on C2. So therefore, that's what you get from here. Okay? And you just compare between, you just add them and add. And then what's going to happen is as follows. So here, you just do the integral by parts, and d. So here, if you integrate by parts, d acts on omega here. Okay, that will give you y8. And what's left? So if you add them at 1 minus alpha here and alpha here, so the alpha cancel, and what you're going to get is this guy. And here you do the same thing. So if you do the integral plus d acts on omega 3, that will give you x4. And 1 minus alpha and 1 minus alpha cancel. Okay, so they cancel each other by integral by parts. And what's left is this guy. Okay, and if you be careful about the sign, the relative sign is some number here. Sorry, some number 2 pi 1 minus alpha or something. My lecture note is not the precise math, which means. So I have to do a precise computation, okay? Okay, then this is the case, okay? So therefore, if delta C2 is equal to mu 2, sorry, I think it is plus sign, minus mu 2, this is equal to 0. Okay. Therefore, this is called Green-Schwarz cancellation. Then this delta W tilde is equal to 0. Okay. So this is called Green-Schwarz mechanism. Green-Schwarz cancellation or Green-Schwarz mechanism. So the essence is that all the essence is really coming from I12. So anomaly polynomial, it can be factorized to the let's see, 4-degree cohomology group and then 4-degree 8-degree cohomology element. So you factorize the 4 plus 8. 12 is equal to 4 plus 8. That only when G is equal to SO32 or E8 cross E8. Only this factorization occurs when gauge group is SO32 and E8 cross E8. And if you solve all the descent equation, if you add, then you can add this counter term. And the C2 is really the type 1. Ramon form. So it couple to D1 and D8, D5. Sorry, D1 and D5. Okay. It couple to D. So this is the Ramon C2 form, and the other is characteristic classes. If you add a counter term, one can cancel this anomaly. And if you trace back what's going to happen in the, so here, it turns out as follows. Okay, so there are lots of typos. So here, from here, one can just show that the DC2 plus omega 3. So lots of is gauge invariant. It turns out from here. So if you look at this one, if you act on D on it, delta B, and D acts on C2 is equal to plus D mu 2 is equal to 0. Okay? And we know that the D mu 2 is delta omega 3, right? Delta omega. So therefore, delta B, BC. So I just act on that what I'm doing here. Sorry. Yeah. Now from here to here, I just act on accelerator D. Yeah. So yeah, accelerator D. So then D and delta will commute. So delta be D, and the D acts on mu is just this one. And we know that D mu 2 is equal to omega delta omega 3. So this is 2 plus omega 3 is equal to 0. Okay. So therefore, this is the gauge invariant quantity. So delta B is a gauge transformation. And then dC2 plus omega 3 is a gauge invariant quantity. And then if you are really like a astute students, you notice that in supergravity term, we have this kind of combination. In supergravity action, we have this one. We define like this way. This is equal to dC2 plus alpha prime over 4. This is normalization constant, and this is the trace of ADA plus 2/3 A cube minus trace of omega d omega plus 2/3 omega cubed. So this is the case. And this gauge term will appear as the supergravity action of type 1. So if you look at the type 1 theory, type 1 supergravity action has this kind of like a S is equal to R plus, roughly speaking, this way. I'm not going to repeat, but G3 tilde square. This term will show up. I don't remember the overall normalization, e to the some phi or something, minus phi, and then dx, d10x will show up. And this G tilde 3 is the gauge band quantity, which is really coming from this Green-Schwarz cancellation. Okay, so that's what's going to happen. It's really miraculous. So as you can easily see, omega 3 is up to some constant term, which I'm not careful. As you can see, so this omega 3 is really the trace of Chern-Simons of the spin connection and trace of the Chern-Simons in adjoint representation. Minus 130 is actually cancelled once you replace adjoint to the fundamental representation. Actually, trace of adjoint is 30 times trace of the fundamental representation. So there's a 1 over 30 cancel, and you get the correct coefficient. Okay, so that's the Green-Schwarz cancellation. It's a super magical. And then what are the interpretation of this counter term? So this counter term we need to add to cancel anomaly. Where should I erase? Maybe I will erase around here, maybe? I can erase. So this is the Green-Schwarz cancellation. So anomaly can cancel. Is cancel only when G is equal to SO32 and then or E8 cross E8 by adding the counter term, a Green-Schwarz counter term, Green-Schwarz counter term, or Green-Schwarz term, counter term. What was that? That one. Gamma and then minus 2 pi, 1 minus alpha d omega 3, which omega 7 plus C2, which 8. Okay. So this is actually higher derivative. It's called higher derivative correction. Higher derivative correction. Tip correction to the type 1 supergravity action. So type 1 supergravity is a low energy effective action of the superstring theory. Okay? So you just integrate out all the massive mode, massive contribution, integrate out by path integral, and look at only the massless field, the contribution. But this, if you compute all the quantum correction, always you have the higher derivative correction, and then you will get this kind of term. And this higher derivative correction is really cancel this anomaly. So it's a magical cancellation. And what's moreover, so this C2 is actually Ramon 2 form. And then this Y8 is already written over there. So this is it depends on F. This depends on F. This depends on R. This depends on F. And this is R and R. Okay? So it's a mixture of F and R. And this term is indeed corresponding to C2 is like this way, and then there is a full graviton or gauge field appeared, and then there is some two contribution. It's coming here because of it has to have the 12 hole, and this will cancel. This will cancel with this hexagon anomaly. So that's what's going to happen. So people, if you look at the Green-Schwarz paper, this kind of like a diagram will show up, and it's cancel with this Green-Schwarz coupleton because of this higher derivative correction to supergravity. So yeah, the upshot is that so if you just the main point is really only when the gauge group is this one, the anomaly polynomial factor is 4 plus 8, and if you solve this integration, that can be cancelled with the massless field in type 2 field, type 1 field, by adding this counter term. Yeah, so this is 84. And then 85 or 86. 85 or 86. So we know the SO32 will work for type 1 superstring theory. And what's the meaning of E8 equals E8? And that will appear as a heterotic supergravity. Okay, so we know that the type 1 only can have SO32 gauge group. But for heterotic, where should I erase? Maybe I will erase around here. Heterotic, so we know that, so we already knew, just give within, and the great people give us an answer to A to B type 1. This is SO32, and its SDL is SDL is heterotic O and heterotic E. Okay, this is SDL. They are related by SDL, SDL and TDL. And then here you have a C2, right? So you have a C2 field, and if you do the SDL, what kind of field it become? B2, yeah, B2. So C2 is coupled to D1 and D5, and this B2 is coupled to what? F1 and then NS5. Okay. So in supergravity, so this anomaly cancellation analysis, instead of C2, you replace by B2 in heterotic supergravity. That's it. You just replace C2, and just be careful of normalization. Then heterotic supergravity is also counts anomaly, and then HO, the supergravity action is almost same as type 1. You just exchange C2 and B2. You just name it differently. This has SO32, and this has E8 equals E8, and then this anomaly cancellation would really tells us the superstring incorporate this anomaly cancellation, even for E8 equals E8, since the Harvey-Cullen, I forgot the name, Cullen, Harvey, blah blah, who show that there are additional two superstring 3. Holomorphic sector is the superstring, and bosonic anti-holomorphic sector is the bosonic string. Is also a heterotic string. Can incorporate this gauge group. And then yeah, so before 84, only people know 2B and 2A, 2A, and type 1. And this, so Alvarez, Gaume, and Witten show that these are anomaly free. And type 1 is anomaly free by Green-Schwarz. But Green-Schwarz predicts that there is an additional gauge group will show up in string theory. And then year after or 2 years after, heterotic O and heterotic E is constructed. and so this is HE and HO will be constructed. So therefore, 5 superstring will be constructed around this time. So around this first string string revolution. So that's a history. And they are related by duality. Those are the we have to wait the genius of the within in 95. Okay, so let's take a break, and I'll talk about D-brane after the break. Okay. Objection. Can you have the solution 10 and solution 11?
Yes.
Are you editing?
Solution 10, I asked the thing. I'll do it this week, next week. Because last homework I still haven't graded the last homework.
Okay. Yeah. Please do it immediately. Did you send also email to students who didn't submit?
Yes, but he didn't reply.
Do you know his WeChat? I already sent a WeChat message, but he must be in the group chat, but I don't know which one is he. Okay, so shall we resume? Okay. Fine. let's talk about D-brane to some extent. I mean, it's a deep subject, so I mean, we can just take only peek or glimpse at the D-brane, but I think it's worth doing that. Yeah. Okay. So I just want to make a comment about the Green-Schwarz anomaly cancellation. We only need to take a look at the 10 dimension, but the same thing one can do for 6 dimension. 60 supergravity. So you have to take the, see if it is supergravity is 6 dimension, what is the anomaly polynomial, degree of anomaly polynomial? Should be. So 6 plus 2 is 8. And then we have this kind of Green-Schwarz anomalies can occur by just factorizing 4 times 4 plus 4 and so on. And here you again have a chiral fermion. I don't know, it involves chiral fermion, gravitino, and dilatino, gaugino, and also self-dual. Self-dual form will show up because it's and self-dual field can contribute to 4k plus 2. Or its space dimension is 4k plus 2. So therefore, if the supergravity, if you just do the contribution from this field, and it can be factorized, even though adding them up do not count, goes to 0, if the factorization occurs, you can have the similar kind of like Green-Schwarz anomaly count. If you have this factorization occurs, even 6 dimension degree Schwarz cancellation will occur. So that's even 6 dimension that is a case. So that's one comment about the Green-Schwarz cancellation. And this anomaly polynomial is very, very useful actually. It not only, I mean, some people, like, I don't know why, but some people hate string theory because some physicists hate string theory because it doesn't have a practical application. It's not does not describe whatever nature and so on. But that's fine. I mean, it's also criticism are kind of legitimate. But this anomaly cancellation, you're just starting with the this anomaly polynomial and do the look at the anomaly cancellation and so on. These techniques are already used in condensed matter physics. So technique, whatever, Green-Schwarz or whatever, Alvarez Gaume and Witten did for anomaly analysis of string theory can be used in the condensed matter physics. So anyway, so that's the case. So even the technique we have developed, not we, the great people in string community did, can be used, can be used for the other subject. Okay, let's talk about D-brane. So I'm going to talk about D-brane slightly. So apart from today, there are 2 more lectures supposed to be. There are supposed to be 2 more lectures. Okay. Okay, maybe after D-brane, maybe I can talk about some introduction. It is 50. That's okay. So, but before that, let's talk about D-brane. So far, we just treat D-brane as the boundary condition of the open string. So far we just but it's dynamical. In fact, it's dynamical. It's dynamical. It's a really dynamical object. So therefore, it should have some kind of action. Some kind of action. Yeah. So what is the feature of D-brane? So it's indeed dynamical. Indeed dynamical. Dynamical. Dynamical means that it can fluctuate. It can be creation, annihilation, or annihilation. Sometimes decomposition. Lots of like a dynamical thing occurs in the decomposition. So the D-brane can fluctuate in space-time. Also, somehow D-brane will be created or annihilated. It's just one D-brane just annihilates, splits into two D-brane and so on. So this is a really dynamical object. So therefore, it should have action. So so far, the feature we look at as follows. So we want to write down the action. So we want to write down the action of the D-brane. But what are the features? First of all, you have a scalar as a space-time coordinate. Time coordinate of D-brane. Okay, and also so it should have a gauge field. You should incorporate gauge field because I mean we know that if you have a stack of D-brane, you should create a Yamir's field. That's what we already learned by TDLT and so on. And also it should involve the involve B field because open string can end on D-brane. Okay, and also it should be coupled to Ramon CP plus 1. And also if the brane configuration nice enough, it preserves supersymmetry. Okay. So those are the features of the D-brane so far we look at. So we try to construct the bottom-up approach to construct. So that this action is often called DBI action. Action. So what's DBI stand for? Do you know? So Born infeld, I forgot the D. Dirac? Okay. So Dirac Born infeld action. I don't know why it's called Dirac Born infeld. I don't know why. But anyway, if you know, just tell me. Okay. The first of all, so let's recall worksheet action. Worksheet action is something like I forgot D squared sigma G mu nu partial A x x mu partial B x nu and then HAB. That's the worksheet action up to some number. But before going that, we just take a look at the, worksheet, line action is just line segment of the, we want to generalize to the so-called non-Goto action. So this is the D squared sigma square root determinant of the partial A x mu, partial B x mu. So that's the area. So this is essentially the length measured length. This is measured area. Okay. But we don't know how to quantize this. This essentially it depends on the sign signature. In Gaussian Euclidean, you have to add the negative sign. Depends on the area, but we don't know how to quantize. Don't know how to quantize. Okay. We can do the similar thing for the D-brane. So D-brane, so we can start with the action, something like just the measure the volume up to some constant. We call it the effector dP, and then P plus 1 sigma minus determinant of G mu nu partial x mu A sigma A partial x mu sigma B, and this one. So we just consider the space-time is something like whatever x0, whatever x1, x whatever 2 to 9 or 10 or whatever 9 to 25 and so on. And you have a D-brane whose position is given by x mu. The space-time position is given by x mu, but the word volume coordinate is the like this way, 1 to p. World volume coordinate is given by sigma. Since it's a p-dimensional object, so space-time runs for 1 to p, and time direction is sigma 0, and then it sits in somewhere in this space-time. So this is the so the space-time has whatever metric m 1,9, and then space-time metric G mu nu, and then you can just embed the D-brane, and then this is indeed the Pubac. It's called Pubac metric HAB. I shouldn't use HAB maybe. Anyway, the metric Pubac of xg. Pubac metric is I don't know. This is a metric induced on the D-brane from outside of the wall. Okay, and then take the determinant and take a square root. You get the volume of the D-brane. So we can just we don't know how to do that. How to quantize? We don't know how to quantize. But that's a good candidate for it's a Navigator action of dp brane. Okay, but we can slightly here at least we just achieve first goal because of x mu is a scalar. It's just really the x mu is the position of the D-brane. Okay, we achieve first goal, but we want to include the gauge field and the B field from now on. Okay, so this action does not incorporate the gauge field and the B field. Let's do that. To do that, I think we should the best way to think about incorporate gauge field is the consider T duality. Okay. So let's recall T duality. So T duality is the something like this one, and dp brane sits on the S1, and then whatever R. And then so let's consider this one is x1 direction, and this is xp direction, x2 direction. And then here, this space, how to say? So this is D-brane. So it's type 2A or type 2B? Which 2A or 2B? Either 2A or 2B has D-brane. Which theory have a D-brane? 2A. So it should be 2A. And if you take TDL on X2, it can have like this way. D1. So this one is alpha prime over R, and then this X1, and then this is X2. Okay, so that's the case. And since now, so here we can have this x mu can, how to say, fluctuate in terms of Walsh coordinate. So here, so we know that the gauge field here. So the or gauge field or holonomy x. So mu A2. So I forgot the A2. If it is a constant, that should correspond to the x2 of x2 coordinate of the D1 brane. Okay. So x2 is a constant. It's independent of the position of the D brane. So the D brane. So, but you can turn a holonomy or Wilson loop. A2 is a constant. That corresponds to the position of this is the x2 position of the x2 position of the D1 brane. So that's what we have learned in the T-duality section. But now we can just fluctuate. So we can fluctuate this D1 in the x2 direction. So let's consider such as Gedanken experiment. So now, so therefore here we have x2 can be have some derivative. So x2 can depend on x1, and we just set the x1 is equal to sigma 1. So x2 is sigma 1. So therefore you can have such a fluctuation. It's non-zero. It used to be, if it is x2 is a constant, this is automatically 0, okay? Because it's a fixed position in the x1 direction. So, but now if you fluctuate this yellow line, if yellow wiggle line, this is no longer 0. So what's the meaning of here? So that's A2 sigma 1 is not equal to 0. Okay. And then this is included inside F21 in the gauge field. Okay. So therefore here, which means that if gauge field strength is no longer 0, which means, okay. So before we consider turn on the Wilson loop means A2 is some constant value. Gauge field constant value along this space-time of the wall volume of the gauge, the D brane. And if you take this constant part of the gauge group, it will tell you the position of the D brane in TDL side. But if you fluctuate this D brane, which means that on the TDL side, it just turns on the field strength. It has an electromagnetic field inside the D brane. So that's what it means. Inside the D brane. So we can just do the following thing. Okay, So the SD1 is equal to minus effective D1 D squared sigma like this way. So, and then this can be understood as the minus T effective D1 D squared sigma, and then minus determinant of 1 plus like this. So one can just take like this way. Sorry, it's after determinant, sorry. After determinant like this way. Square. So essentially this x mu and x nu, so this sigma is the essentially 0, it's D1 brane 0, 1, and we just have this like, okay, so this is the determinant. Most likely there's a minus sign here, I don't know. Let me think about it. Sorry, what am I doing here? There should be 1 plus. Yeah, 1 plus. And the minus sign here. Okay. Do you understand what I'm doing here? So I set the so this one is the this one is matrix. How to say? P plus 1 matrix. The coordinate is really the coordinate. Okay, let's go HAB. So it's AB intercept. This is matrix, and mu coordinate is a contracted. So therefore, it only depends on small a, small b. That is a volume coordinate of the dp brane. So it's HAB. And now I take H0 is equal to sigma 0. And then H1 is equal to sigma 1. Okay? So then this part is the only see the first component 0, 0, 0 component is only see x1, and then so mu equal to 0, mu equals 0. And since it's what was that? Minkowski signal, you have a minus 1 because, and here 1 plus del x2 squared, sorry. Square is indeed 1 is x1 sigma 1, x1 sigma 1. So this 1 is really del x1 del x sigma 1 del x1 sigma 1 inside this component, and which is 1 because I just set this one. But in addition, you have an x2 fluctuation. We now consider yellow brane, so it just fluctuates the x2 direction. Therefore, that is non-trivial. That's why you get this. Okay. Anyway, so that's what I have done. And let's compare the action of the SD2. And this is minus D2 effective the cube sigma, and minus determinant of G mu nu partial x nu sigma partial x nu sigma b. And then this is not enough to compare with this one, because now we know that the here this part where's the color choke? Oh yeah. This yellow part can be translated into the gauge field here. Gauge field, field strength of gauge field here. So we have to add some gauge field with appropriate normalization. 2 pi alpha prime f AB. So we have to add this term to compare with the under the TDRD of the D-brane action. Because we already knew that it's a space, x1 and x2 direction is space filling. So this is will give you 1. This will give you 1. So therefore, this is TD2. 2 pi r and then F12 sorry. Determinant should be included in everything. Sorry. Okay. So then one can compare between the actual D1 brane and D2 brane. Okay. So therefore, in addition to the Nabu-Goto action, we need to include FIB in the D-brane action in the presence of gauge field. So that's what it means. So the second goal is achieved. Now, since we include FAB, gauge field second goal is achieved. Second goal is achieved. Okay, so that's the case. Before going to the talking about the B field, we just need to talk about what's this T. The overall coefficient. So this T is indeed is the D-brane tension. So therefore, essentially, this will give you tension times the volume, which means that this will give mass of the D-brane. Okay. So we know that in the previous cases, TDP. Here, so M theory have the D2, M2 and then M2 and M5, which has 2 pi L Planck times 2 pi. I already forgot what was the power should be? I forgot. Sorry. I think I should take a look at my lecture note. Sorry. What was I should have known that. Does anybody remember? Anyway, so and from here, 2 pi LP, and from here you get the actual dP has the tension has the 2 pi times 2 pi ls p plus 1. So most likely my guess is the 6 and this is 3. Okay, 6 and 3, and I hope it's correct. Let me check now. Here it is, and hopefully I was correct. Here Planck length, and this is string length, and then that's what we have deduced. And then we just compare what is the effective D1 and D2. So another TDRT, so here in fact, so it's most natural to expect to have the dP as in fact this TDP. No, effective one is given by the P plus 1 sigma e to the minus 5. Phi is the what the fuck? Let's see. G mu partial x mu partial sigma a plus x mu partial x sigma b to pi alpha prime f a b. Okay. So it's most natural to incorporate. It's kind of ad hoc to incorporate dilaton field of x. Because I mean here it just gives you some the action for this temperature for open string worksheet. So this amplitude is proportional to e to the minus pi. Okay, e to the minus pi because of the Euler characteristic like this way. So this one, and also under the T reality, this we know that the phi tilde. Under the T reality, phi tilde is transformed like a e to the minus pi r over ls. Okay, so that's how it transforms under the T reality. But then the compare between these two, we know that 2 pi r is given by TD1 effective, TD2 effective. So as you can easily see, if you compare between these two, okay, compare between these two, so this T D1 effective, it should be equal to, sorry, I forgot to write the effective, TD2 with 2 pi r, okay? So 2 pi r is really coming from the S1, DD3 S1, and S1 is this direction. The how to say, circumference of the, it's called perimeter? I don't remember. Perimeter length or circumference of the S1 direction. That will give 2 pi r, and times this one should be equal. So now for 2 pi r is D1 effective and D2 effective tension. And we know if you incorporate the this dilaton field, this should be TD1 D minus pi, and then this is TD1 D2 E to the minus pi tilde. And then this is equal to, if you plug this one into here, this one is equal to TD1 TD2 is R over Ls. Okay, R over Ls. Okay. So therefore, this means that this will tell you that the TD1 should be 2 pi Ls times TD2. Okay, TD2, and that is consistent with this one. So therefore, this TD1 is equal to TDP is equal to 2 pi Ls square, which is 2 pi Ls TD2. Okay. So like this. So this is consistent. So this means that it's in. So here, so the lesson we learned is it's natural to incorporate this one, e to the minus pi of minus pi, and then T effective is essentially just scaled by e to the minus pi, with the tension coming from it, M3. Okay, so that's the case. So we incorporate the correct normalization for D-brane action now. So now we move on to B field to incorporate B field. Okay, B field. So that's actually very easy. Actually, in string theory, in order to the gauge invariant, 2 pi half. This is a general lesson. F plus B will show up as combination. Should show up. So this is a general lesson motto in string theory to be gauge invariant. Gauge invariant invariant. Okay, so that's the case. So that can be seen from the worksheet action of the open string. And in fact, just give you the answer first. So SDP is indeed given by TDP. So I just give you first the answer. Why this is the case, I will explain later. So dp plus 1 sigma e to the minus phi, and then minus determinant of partial x. I'm not going to write down the detail. The 2 pi alpha prime FAB plus BAB. So this should be the case. So this should be the case to incorporate the BPO. So therefore, it can just and open string can end. So just keep it on there. And in this way, so this one is achieved. This one is achieved because of this guy. So why this is supposed to be the case? This is the case because why this is the case? So because open string, its open string has the usual action. Do you remember the usual action of the square root HAB partial x plus whatever BB new partial S B and then alpha prime square root H. So that's we already learned a long time ago. We learned like already. Okay, it's amazing. Time flies. It's this kind of action already we learned in March. March is already almost 2 months ago. 2 months ago, and since it has a boundary, it should have the following the Wilson loop term at the boundary. D sigma 0 partial 0 x mu and a mu. Okay, this is sigma and the boundary of sigma. So you have, so now open string worksheet has a boundary. Okay, has a boundary like this way, and this one is sigma, and the boundary of sigma is like this way. In the boundary of sigma, you should have this kind of Wilson loop term at the boundary. Okay. And if you look at this one here, it's just a pullback of B field into the. This one is pullback of B field to the sigma, and this is pullback of gauge field to the boundary of sigma. And then if you consider the gauge transformation of the B field, so we know of the gauge transformation of the gauge field. So gauge transformation of the gauge transformation of the B gauge field is like this way, and abelian gauge field is like this way. Okay. For B mu, two-form field is transformed like this way. Whatever, lambda nu, and the minus nu, lambda mu, and lambda mu is a one form, or dx. Okay, lambda is a one form. Okay, so that's our gauge. The B field should transform on the gauge transformation. Okay, in the form, it should be transformed like this way. It's transform B2 plus d lambda 1. Okay. Lambda 1. Okay. So therefore, under this gauge field delta B, so I call it this delta B. Delta B B field is equal to dA d lambda 1. And since this action is open, contains like this way B2 plus number of A1. Okay. So this is a worksheet action. So this part is actually the pullback of B field to the worksheet. Okay. This is a pullback. Which one? So this part is a pullback of B2 on the worksheet. And then this guy is a pullback of one form to the boundary of the worksheet. This is A1. Okay. And in order for the action to be gauge invariant of the B field like this way, we need to have delta B. So therefore, this sigma of B2 is under gauge field transformation is like this way, become plus boundary of sigma by Stokes theorem, like this way. So this means that so we need to have the delta B. Sorry, I think there is some normalization occurs. It's open. It's a 2 pi alpha prime somehow. So therefore, we should have the delta B of A should have lambda 1. So therefore, sigma of A1 is transformed to delta sigma A1. And then 2 pi alpha prime minus. And then appropriately 2 pi, so everything 1 over 2 pi alpha prime, 1 over 2 pi alpha prime, 1 over 2 pi alpha prime. And here also have a 1 over 2 pi alpha prime. Okay, so therefore they should cancel. So both cancel by under the gauge transformation of the B field. Okay, so therefore, so this combination is really gauge invariant in terms of the gauge invariant of the gauge transformation of the delta B. So it's not usual gauge transformation gauge field. It's a gauge transformation of B field is like this one. So therefore, in string theory, the general motto is the 2 pi alpha plus F plus B should show up under the gauge transformation of delta B. Be careful, there's delta B is not the BRC transformation now. It's a gauge transformation of B field. This is general motto in string theory. So therefore, if you have F, you should have a B in the in the worksheet or D-brane. So therefore, this is the most covariant way of writing the Navigator action in the for D-brane. Okay, so we have achieved the 3 goals, and now we incorporate the 4th goal. Okay, 4th goal. So that's how I'm going to do that. Before that, I wanted to remind you something. Yeah. So Navigator action is indeed the mass of D-brane. First, we start to get this one. We start from Navigator action for the. We start with something like a dP is equal to minus d effective. dP is the sigma p plus 1 sigma minus determinant of partial x, partial sigma a, partial sigma b. So we start this one. This is the, as I mentioned, this one is a volume of dP brane. And this will give you tension, effective tension. If you mass by volume times tension, what you get is a mass of. So the action is essentially roughly speaking mass of dP brane. Okay. mass of dp brane. But that's kind of natural, right? When you consider action and so on, I mean, you just consider the energy as an action. So it's kind of natural to consider. So, but if you incorporate these three factors, what you end up with this guy. So this is the most covariant way of writing Navigoto action for the dp brane. Now, we just consider the Ramon field. Okay. Ramon field. And previously, we already knew that the so in previously when we considered so if you have an electron moving around the space-time, we have the dA mu in the dA mu in the worldsheet in the world line. So we have this coupling. So we generalize this one to the dp brane. We have a dp brane, whatever. dp brane is just transform under the moving around the space-time. We have mu p, dp, and cp plus 1. So that's what we have considered previously. And from there, from here, we just consider the so-called Dirac quantization condition and so on, and to determine mu p, how the mu p should be. Okay. And we want to actually so generalize this one by just considering these two facts. And again, we use T duality to generalize this Ramon. So this is called Ramon coupling. Ramon coupling term to the dp brane action. So to generate this action, we again use the T duality. We again use the T duality. Okay. Oh, it's going down. Okay. So for to do that, I think we just write down in the coordinate the Cp plus 1 is indeed given by sigma and then C mu 1 total. I mean, just the physicist way of writing. Physicist way of writing the differential form. Okay, like this way. And again, what's going to happen in T duality? Again, the dp, d2, space-time d2 is T dual to d1 brane, x2, and then x1, and this is whatever, r, and then alpha prime over 2 pi r, like this. So once you start fluctuating this one, okay, once you start fluctuating on x2 direction, we know that this has f12, okay, we know f12. Once you fluctuate this one, we know that there is something non-trivial happening here, okay? Because I mean, x2 can be have a non-trivial derivative. So now we know x2 of sigma y is not 0, okay? So that's what we need to incorporate. So therefore, so if you look at this side, people call S Ramon. dp. Okay, Ramon. dp is something like mu 1 q. Okay, become like this. Okay. Now recall that we put the x0 is equal to sigma 0, x1 is the sigma 1. Okay. So if you put like this way, choose mu1 to be 0 and mu2 to be 1, then you get the first term, okay? And the second term, you put the mu1 to be 0 and mu2 to be 2, okay? Then we know the del x2 and the del sigma 1 is non-zero, so therefore we have this kind of term. Okay, so let's move on to the next. Okay, then, so this is mu1, and then, so let's move on to this part. It's Ramon, and this is D1, and this is D2, this is mu2, and D sigma 0, sigma 0, D sigma 1, D sigma 2, and now we have C tilde 0, 1, 2 plus C 0 tilde. And we should incorporate, to get this term, we should incorporate 2 pi alpha prime f1, 2. Okay? So we have to incorporate this C tilde here. Okay. So that's what we have. Okay, so now we have the we can compare between these two. So we know that under the TDRT C012 is compared with this guy. Because I mean, there's not a TDRT on x2 direction will increase the indices 2 if there isn't, decrease, remove 2 if it increases. So therefore, this is compared with this one. It's different. Okay. Okay, and then appropriate normalization, this guy is equal to f12. Appropriate normalization become this one. Okay, so that's what's going to happen. So therefore, if you compare, if you look at this one, so it's a natural guess one can do is indeed as follows. Is indeed as follows. So if you have a gauge field on the here, we need to. If this means that we need to incorporate f12. This one SDP is equal to mu p SRR, which is exponential. It's like this one. So again, here is the combination, gauge invariant combination. So the general lesson we learned, if you incorporate F, you have to incorporate B. And then here we have the, so you have to do the Taylor expansion. This means that the 1 plus 2 pi alpha F plus B. And then if it is non-trivial, so plus 1 over 2 factorial. 2 pi alpha F plus B square. Square means wedge. It's just wedge product, and the plus dot dot dot. So that's what we need to do. And this is 2 form, and this is 4 form, and so on. And that is naturally coupled to CP. So this is C whatever. Depending on 2A and 2B, you just have the whatever sum of n, Cn. And then here we just only take out the non-trivial p plus 1 form out of here, out of this action. Okay. Okay, so that's the case. So then the action for D-brane is indeed this Navier-Goto action, generalized Navier-Goto action, plus this Ramon coupling, generalized Ramon coupling. So if you add them up, you will get the bosonic part of the D-brane action. So that's what's going to happen. Okay. For soup, if the D-brane has a very nice configuration, it preserves some amount of supersymmetry, and paramagnetic part will show up. But that's I'm not gonna go into the detail. I mean it's kind of complicated. Always paramagnetic part is complicated, but you have to supersymmetrize this bosonic action. So that's the what's going to happen in the action of the D-brane. So yeah, people call it so this is the somehow it's called DBI action. I don't know why. And this is for Ramon coupling. Action for Ramon coupling. Okay. I don't know why it's called DBI. Dirac-Born infant. All people are not involved in development of string theory. I don't know why, but anyways, that's how it's called. Okay, so that's the case. And so far, we just consider only one D-brane. One D-brane, only single D-brane. So therefore, this F is a really abelian field. Okay, it's abelian field. So F2 is indeed dA. So it's just. But if you have a multiple D-brane, it should have a non-linear gauge field. So F2 should be something like a dA plus A wedge A. So that's a case. In this case, we don't know how to write down the action. So somehow trace should be involved. And then so on. I mean, people do not know how to generalize the non-abelian case. It's an open problem. And there are lots of proposals and so on, but nobody has the confident answer so far. Okay, that's the case. Even though if you have action, we don't know how to use it actually. Because we don't know how to quantize it. We don't know how to quantize this action because it's square root of determinant. Even though we write the action, we just do the perturbative expansion and do some perturbative computation of fluctuation of D-brane. That we can do, but it doesn't tell you anything about something interesting and non-perturbativity, which is important for D-brane. I don't know. We don't know how to use even like a general proposal of multiple D-brane. So even though D-brane was, I have to mention D-brane was introduced by 1996 by Polchinski. It's already almost like 30 years past. Yes, right? It's almost like 28 years. Still open problem. Okay, that's the case. Okay, so that's the case. So let's talk about something about the tension of D-brane and so on. Maybe, I don't know. I mean, it's, I don't know. This computation has been done on Polchinski. I'm not sure if it is interesting to. Maybe I can skip and then talk about how D-brane ends on the itself. Okay, I will skip D-brane tension. I think I wrote the D-brane tension. So as I mentioned, D-brane tension, dTp, can be computed 2 pi ls p plus 1. And this was derived by just computing the cylindrical action. This is really original paper. If you, I mean, you guys now learn basics of string theory, so you can now really read the original literature of string theory. So I highly recommend to at least take a look at for instance, Polchinski 96 paper is only 4 pages because PRL. It's published on PR. It's 4 pages. So it's super easy to read. So so he computed this cylindrical action. What was that? How do you write that? So cylindrical action. Okay. Cylindrical action. Cylindrical amplitude. And so he computed cylindrical amplitude to compute. So this is D-brane and D-brane. Since they have a masses, because of tangent, they have masses. Okay, so therefore there must be some gravitational attraction. Okay, in between, and by exchanging cross string. So D-brane, and in the middle you have the whatever cross string, but that is equivalent to the as I mentioned, the open cross duality. Some people call it. So it's just the open string between D-brane is the moving along on a circle that can be computed, and then from there he just obtained this tension of the D-brane. In fact, tension of D-brane. Actually, in fact, so here the amplitude is proportional to this amplitude proportional to what they get is the L string 6 minus 2p, and then 6 minus 2p, and the green 9 minus p of k squared. K is a distance between them. K is distance between them. And this is the massless green function in 9 minus D-brane, 9 minus p. So it's orthogonal to the D-brane. Okay, D-brane, orthogonal D-brane, and then Polchinski mentioned that this should be proportional kappa square dp square and g 6 minus p, so 9 minus p, sorry, 9 minus p k square. So this is a computation coming from the string theory, and from physics they tell us that it should be proportional to the Newtonian gravity. I mean, it can be just computed in Newtonian gravity. So it has a mass here, and they are attracted in 9 minus p dimensional codimension dimension, and therefore it should be proportional to this one. And if you compare between these two, you can deduce D-brane should be like this. That's what Polchinski has done in 1996. It's really readable for you guys, actually. It's now. I mean, it's just what you did in the homework for superstring, Ramon cylindrical amplitude. You just did a homework. So and it's 4 pages. If you read it, it's immediately understandable. So that's how he found the string tension, D-brane tension. That's what they found. Okay, it's yeah. But I'm going to skip that, and then I'm going to talk about D-brane. Can ends on D-brane, but how much I'm not sure if I can go how much. It's kind of like a okay. Maybe I should derive this one. That's also okay, because I mean I cannot talk about this massive 2A supergravity in 10 minutes. Okay, I will derive this one from now. In that case, it's just 10 minutes derivation for you guys. So what the Polchinski did as follows. So if you consider the one loop contribution of particle, so this can be understood so it can be understood one loop amplitude for open string. So for instance, one loop amplitude, amplitude of the massless particle, massive particle. Okay, one loop of massive particle with mass m is given as follows: minus bp plus 1 amplitude, which is 1/2 dp plus 1 k in space-time dimension p plus 1, and log k squared plus m squared. So that's the usual one loop amplitude for so here it's just the momentum integral, and this is the log of essentially Klein-Gordon equation. And then one can perform this Gaussian integral. Minus bp plus 1, and then this can be dt. It's kind of some trick one can perform. dt to 2t, and then dp plus 1. I mean, this is the one way to get the log. P plus 1 and e to d 2 pi alpha prime. Okay, so that's what's going to happen. And then first you can perform this from here to here. You just perform t integral, but before then you can perform k integral by Gaussian integral, which can be obtained as follows: p plus 1 dt 2t and 8 pi square ls square t minus p plus 1 over 2 and e to the minus 2 pi alpha prime and square over 2. That's what you can get from the massless particle from the p plus 1 dimensional body, one loop amplitude. Okay. And then, so we know the mass of open string between them is in fact, so mass is equal to mass square alpha prime is equal to L0 plus k square divided by L square. So alpha prime m square is equal to L0 plus k square Ls square. Okay. So here it's just as you recall, so 1 over Ls, 1 over alpha prime is the tension of the string, okay, and this is 1 over I think it should, I don't remember, sorry. It should be Ls. It should be Ls squared, right? I don't remember, sorry. I think I should go back to the lecture note. I'm correct. So the T of strings is 1 over 2 pi alpha prime, and the alpha prime is string length Ls, square root the other one, like this way. Okay. So therefore, so the mass square is the proportion k over ls and square. Okay. So that's the case where the k is the length between dp brane. Okay, dp brane. And we can take, so therefore we can just compare this one is equal to minus bp plus 1, so I is missing. And then dt 2t, and 8 pi square ls t minus p plus 1 over 2, and q to the k square ls square trace of q to the l naught. Okay. L naught. So that's what's going to happen. So here, yeah. So this, I just plug this one into over there. Okay. And we know that this trace of q to the L naught by in superstring. And this is indeed equal to, in fact, q to the minus 1/2 product of 1 minus q to the m minus 1/2 to the 8 divided by product of 1 minus q to the m product of 8 m rounds for what? 1 to infinity, m rounds for 1 to infinity. So if you're, so here I just use so-called Jacobi identity. I mean, you have to be careful. I mean, here is you don't have a minus sign here, minus 1 to the f. I don't put the minus 1 to the f here, but here you have a minus sign here. So you have to be careful about why this is a minus sign here, because I mean we know the trace of q to the L naught and s sector plus trace of Ramond of q to the L naught is plus trace of minus 1 to the f q to the L naught and s sector is equal to 0 because of Jacobianity. This is theta 2 to the 8. I don't remember, theta 3 to the 8 and theta 4 to the 8, and the appropriate sign should be equal to 0, right? So that's what we already learned. And here we just sum over all possible 1, and then that will give you this minus 1 to the f q to the L naught, in fact. Therefore, so the sum of all the potential boundary condition fermion should give you the ns of minus 1 to the f. I use this one, in fact. And then if you sum them up, it should be equal to this one. Okay? So that I use this one, actually. I already used this one. Okay. And do the manipulation. So do the manipulation. So okay, so it's about time. Do the manipulation. Again, so we know this master's field will show up when this cylinder, this T, it can be understood as the T can be understood as the cylinder, length of cylinder, or time length of cylinder, which means that the T is the circumference of this circle. Okay, this is T is the circumference of this circle. And then when T goes to zero limit, master's field will contribute. And that can be obtained by S transformations. Q is equal to, of course, e to the minus 2 pi t, okay, 2 pi t, and take T goes to zero limit. T is zero limit. That can be done by using S transformation of this one, and then that is indeed proportional to this one. And then compare with this one, and the kappa 10 is coming from supergravity side. Kappa 10 coming from supergravity side. So that's what the Pochinski did of 2 pi. And then to derive this one. Okay. To derive this one, and that is the most famous work of Pochinski in '96. And recently I cite this paper in my recent papers because I use D-brane. And then read the, it's super readable. Yeah, so, yeah. And the citation is almost like already 2,000 or something. Even 4 pages 2,000. It's a very, very efficient papers to get the grant. Anyway, just kidding, just kidding. It's a really great paper actually. But it's readable, so now you guys can read, and this is the essential part of the computation, and to derive this string tensions. And then we derive this string action, and then next week I briefly talk about the string can end on string, and talk about the Hanani with the movement and so on. And after that, maybe I will move on to black hole, ADS CFT, and so on. I mean, unless you want me to talk about something else. If you want, I can talk about this, whatever, 62,0 or like classes or Hanani width and so on. That's also one option. It's up to you. Just let me know if you have a preference. Otherwise, I can talk about the ADS CFT. If you want me to talk about these classes and so on, then I'm fine with that. M5 range and 62,0, that's really I'm working on, so no need to prepare actually. I can just give a lecture. Okay, anyway, let's stop here.